this is Mrs. Ross, and this is the Universal Gravitation Lab. Actually, this is just like the last 4 questions, so I'm going to go through, and you can either pause it or fast forward or what have you. So here we go. For number 1, it says, for sim number 1, calculate the period of the Earth to go around the sun. If the sun had 1.5 times as much mass, confirm your calculation with the simulation. Explain why your calculations don't match up. Okay, so the first thing we need to do is we need to find t, which equals period. And we're going to find period in terms of days. This is what we want. Okay. So on our road to that, we need to find the mass of the sun times 1.5. So that's going to be this. Okay, so we'll take 1.5 and we will multiply it by the mass of the sun. Okay, and then we will do, so the formula that we're going to be using all through this lab is the gravitational force is equal to the gravitational constant G times the mass of the Earth times the mass of the sun over the radius squared, the radius being the distance from the sun to Earth. So I'm going to substitute mass of Earth times acceleration because F equals ma. Everything else is going to stay the same. Now, when I solve for acceleration, so solve for acceleration, and I go to divide both sides by mass of Earth, that's going to cancel out, and I end up with acceleration is equal to the gravitational constant, which is right here, times the mass of the sun, which we have here, over radius squared. So the radius is right here. And that gives us a number that we're going to use. So let me get another color. Okay. Another formula we're going to use, or another formula for A, we have A is equal to V squared, that's a V, over R. I believe that's angular velocity. So we're going to use this to solve for V. So to get V, that's a V, we need to take the square root, because V is currently squared, of A times R. So here is the A, and R, again, is right here. So this is going to give you a velocity in meters per second. And then you have the velocity is equal to 2 pi over 2 pi r over t. So we need to solve for t. And that's the whole purpose of the problem right here. Okay, solve for t. So if I solve for t using this, I'll get t is equal to 2 pi r over velocity. So this velocity is going to come here. You've got it. We're going to use this as our r, and you end up with an answer that is in seconds. Okay, I'm going to scroll down here just to, yeah, I'll scroll down, and I'll have to erase this before I do the next one. But once you have t in seconds, whatever that is, to get it to days, you're going to have to divide it by 60 seconds equals 1 minute. 60 minutes is equal to 1 hour. 24 hours is equal to 1 day. And that's going to give us t in days, because our seconds are going to cancel, our minutes are going to cancel, our hours are going to cancel. So we have days left. So you'll take your t in seconds and divide by 60 times 60 times 24. And that should give you your t in days. So I'm going to pause, erase, and talk about number 2. Okay, question 2, it says for simulation 4, calculate how far the satellite is from the Earth's center. So for this, we're going to use t is equal to 5,400 seconds. And that's not what I want. Okay, so, and we are going to use v is equal to 2 pi r over 5,400. You've seen this before. That's our t. So that's going to come up again. Let me pick a different color. Okay. So let's start off with our gravitational force is equal to our gravitational constant times mass of Earth, the mass of the sun, over r squared. Remember, all of these are up at the top of your page. I'm going to substitute the mass of the sun times acceleration, and everything else is going to be the same because F is equal to ma. Okay, and then when I go to solve for acceleration here, the masses of the suns cancel, and I get this. So I have the gravitational constant times the mass of Earth over r squared. And we are actually looking for, where do I put this? Look for r. Okay, so we're solving for r. So we have this. Okay, let's get a different color here. The other thing that I know, if I substitute for a, then I can get v squared over r is equal to g mass of Earth over r squared. Okay, cool. And then if I multiply through by r, this is going to go away, and one of these is going to go away. So I have v squared is equal to g me over, sorry, that's e, over r. Okay. Then what I'm going to do is I'm going to substitute this into this. So I have 2 pi r over 5,400 squared, just like that, is equal to the gravitational constant, me, and over r. Okay? This is going to give me, let's see, so, let's see. I need to solve this for r. Because this is going to give me 2 pi squared, 5,400 squared, and r squared. So if I multiply again by r to get rid of, I can multiply here. I try to get it out of this. If I multiply this by r and this by r, then I'm going to end up with 2 pi, that's squared. This is r cubed over 5,400 squared is equal to GME. And if I solve for r cubed, I'm going to get GME times 5,400 squared over 2 pi squared. So to get r, I'm going to have to cube root that. And you have all of these numbers, so it's just a matter of plugging those numbers in. And what you get is going to be kind of a big number, but it's going to be in meters. All right, I'm going to pause this and erase it and go on to number 3. All right, this might have to be 2 parts. I'm getting close to the end of what I can do. So for problem 3, it says use mathematics to explain why the moon moves, but the Earth does not appear to move. So if I do the gravitational force is equal to G, the mass of the moon times the mass of Earth over the distance from the moon to Earth. And I plug this in, so you're going to solve for this. All of these numbers are up there at the top of your page. So you're going to get a number here for this. Okay. Then we're going to, let's see. Yellow is not the right one. Okay, here we go. So we know that the force of gravity is also equal to ma, or the mass of the moon times A. We're going to do the mass of the Earth here in a minute. So we're going to plug this in here, and then we're going to plug in the mass of the moon, and we're going to solve for A of the moon, the acceleration of the moon. Okay, then we're going to do the same thing, equals ME acceleration. And we're going to take our force of gravity and plug it in there. We're going to get this from up above, and we're going to get the acceleration of Earth is equal to something. Okay, so the acceleration of gravity for Earth is how much less than the moon's acceleration of gravity. Okay, and I think I can fit this last part in. It says, Simulation 1, Problem 3, Part B, asked how force of gravity would change if the distances and masses of one another changed. Explain using Newton's gravitational law formula, which is right here. So the formula shows that as mass increases, the gravitational force does what? Increases or decreases. And then as radius increases, the gravitational force does what? Increases or decreases. All right, let me know if you have any questions.